so visit again here KIAS. So this is the second time. So I guess totally this is the seventh time to visit Korea, your country. So I'm very happy. So today I talk about this is a joint work with Yuta Nozaki. He is a postdoc in Meiji University, Japan. Okay, so I don't know so what terms you know well or not, so but fundamentally in this talk, so everything I shall explain later. So roughly speaking, so in this talk, so M is a compact three-manifold, and we consider a representation of the fundamental group into SL2C. So always we consider only irreducible representation. So I give a definition later, so but Reidemeister torsion, Reidemeister in this talk we write tau rho m. It is a complex number. So it is invariant of m and rho, a pair of m and rho. So then it gives a function on representation variety for any representation. But so today we consider only reducible one. So then we write for any representation we get some complex number. Then torsion, it is a function on the space of representations. So I shall explain later again these terminology and notations. So torsion, it is invariant by taking conjugation. So then it gives a function on character variety. So then in this talk, we want to consider the image of this function. That is RT, we write RTM. This is the image of tau xe into C. Of course, this is a subset of the complex numbers. So the motivation is the following. So first example. If M is a Seifert fiber space, at that time, so in some sense we can compute tau rho m, so it can be completely computed by using can be computed and expressed by using Seifert index. For any representation. So as a consequence, so if M is a Seifert, so at that time RTM, it is a complex, it is a subset of the complex numbers, but always it is a finite set. So in particular, so if M has many singular fibers, n singular fibers, so if n is greater than 4, at that time, character variety has a positive dimension. It means there exists infinitely many characters, infinitely many contiguous classes, but the image is a finite set. So, in some sense, yeah, in fact, this is theme of my master thesis. It is studied a long time ago.
So in general, the torsion of Seifert fiber manifold also depend on choice of basis of homology. When you
no. So in this setting, so we consider SL2C representation. So now it acts on two-dimensional complex space.
Yes.
So now we consider twisted homology, but twisted by law.
Yes.
So the generic generic representation, this is acyclic.
So irreducible condition imply that H0 and H3 are trivial.
Yeah.
But it also implies that H1 and H2.
Oh, of course. So yeah. So probably you know as well. Yeah. So for example, yeah. So Briscoe manifold.
Yeah.
No. Okay. Not good. So there are many singular fibers. So at that time, so of course, character variety has several connected components. So some of them, so every representation, they are acyclic representation, and so there exists some component for every component, for every representation. It is not acyclic. So then, I mean, so for acyclic one, so we can compute by using Seifert index.
But somehow I think the dimension of the character variety is the same as the dimension of first homology, right?
But
First homology.
Yes.
So
Yes.
that you assume that the dimension of the character variety is non-trivial, then that.
Yeah. So, but now the point is, if you consider combined with adjoint representation, at that time, so first homology or first cohomology of this coefficient, it is the tangent space of the character variety.
Okay.
So, but
You are using different.
yeah, different one.
Okay.
Yeah.
Okay. I see.
Okay, so and the next example, so we consider finite knot. Something like this. So we consider the exterior for one. I mean the complement of the open tubular neighborhood of this knot. This is a compact three manifold with a torus boundary. So in this setting, in some sense, we can compute the same torsion. Simply, we can write it. Two times 1 minus trace of a meridian element. For the finite knot case, character variety. So dimension of this is just 1, and in some sense, freely we can. So the representation, it can be moved in the complex plane. Of course, there are some exceptional points, so that by concrete computation, we can see RT double of this manifold. This is just the whole complex plane. So then, so in some sense, the next problem we want to consider when RTM is a finite. Yes. So now we consider only irreducible representation. So then now we assume, of course, XL M is not empty set. So then now from here we consider only homology 3 sphere. So by Raphael Zentner, he proved for any homology 3 sphere, XL M is not empty. Of course, there is some long history, so but finally he could prove for any homology 3 sphere, so character variety is not empty. So then, of course, in the case that XL is finite, automatically RTM is finite. So then we want to consider the case that XL M has a positive dimension. So then we consider a splice. So I consider the double of the not exterior. So now, in some sense, okay, so we consider two nodes. And we consider not exterior of them. They are compact 3 manifold with torus boundary. So then in this talk we write sigma K1 and K2. That is the 3 manifold EK1 attached with EK2 by using some orientation preserving homeomorphism from boundary of K1 to boundary of EK2. So, which is given by meridian of K1 maps to a longitude. And longitude goes to a meridian. So that is a splice or splicing, so we call it. So the point is, so meridian, it is a generator of the first homology of EK1. So it goes to the longitude. So now, so longitude means this is the preferred longitude of K2. So then homologically this is trivial. So then generator goes to the 0 element, and generator, it is coming from the 0 element. So totally, so this splice manifold, this is a homologous sphere. So from a viewpoint of KIAS invariant, SL2C KIAS invariant. So since you cut this, she defined for homologous sphere SL2C KIAS invariant, which is lambda SL2C M. It is the algebraic numbers of contiguous classes. How to say? This is a number of isolated points of X in them. So original KIAS invariant, so in SU2 representation, at that time, if there are several connected components which has positive dimension, we have to part up to get the isolated points. So that cut is the definition in SL2C. So just we see isolated points of the character variety. So then after Borden and Curtis, they proved for any splice for any two nodes, lambda is set to C, it is always balancing. But on the other hand, so Zenton approved X yield sigma K1, K2, this is not empty.
Question?
Yeah.
Just the count is
Algebraic count.
Algebraic
Sorry,
count.
yeah.
Depends on orientation.
is sign or of course yeah.
Yeah.
I understand, yeah. Okay. This is
So-
not real count, algebraic count.
Yeah. So,
Yeah.
but this is algebraic variety over the complex number.
Yeah.
So then, algebraic intersection, it is always positive number.
Yes.
Yeah. So, but algebraic counting. So, but yes.
There might exist isolate representation.
Yes.
Yeah.
So,
So that invariance does not depend on the orientation of M. You change the orientation, you get a different sign, or
The sign is just intersection.
yes, it depends on representation and orientation. Yeah. So, but now we see this invariant is 0. So, but the character variety it is not empty. So, this means for any component of X yield has a positive dimension. I mean, any point, any component, so it is a non-compact connected component in X yield M. So then,
So my question was that actually we cannot say those statements because there might exist isolated representation,
yeah,
even though the algebraic count is 0. So how can we say that every component has positive dimension?
yeah. So by computation of them,
Yes.
we can see this is 0.
Yes.
So this means, so now if several isolated point,
Yes.
so but the algebraic intersection always it is positive. So then totally it is 0.
Okay, I see.
But this means so we have no isolated point, just several non-compact components.
Okay. So there is no negative.
No negative one.
Yeah, okay. I see.
So yeah, this is the difference between original KIAS and invariant. Original KIAS and invariant, so of course there are several intersections and there is a possibility to get negative intersection numbers. So then, now, the splice of K1 and K2, so let's see. Dimension is positive. So then we want to consider the torsion on this manifold. It has a meaning to do. So in general, so for the moment we don't know. So but with Yuta Nozaki, so we can say the following. So this is the main theorem. So there are several conditions we need. Suppose K1 and K2, they are satisfy the following. First one, for any irreducible component of X in Ki, first condition is dimension of C is 0 or 1. And the second condition is if dimension is 1, then the image, so now we consider the so this is just the torus boundary. So then if we have a representation of EKI, so we can restrict to the boundary. So it induced the map from XL KI to XL boundary EKI. So the condition is if dimension is 1, so C is a irreducible component here. So the image of C never be a point, so that is the second condition. I mean, so the image of C, it has a dimension in this character variety of the boundary of EKI. And one more condition, A-polynomial. So great common divisor of EK1. This is A-polynomial of I will define later, so that A-polynomial of AK1 and A-polynomial AK2. But now we consider a splice, so then we change variable AK to M and L. The assumption is great common divisor of them is trivial. Then RT sigma K1 K2 is finite. So in some sense, so they are technical conditions. So, but first we want to see the next corollary of the theorem. So we get corollary. So if K1 and K2, they are two-bridge knots, then RT sigma K1, K2, it is finite. Yeah. In some sense, we can see K1, K2, they are to bridge. Then we can check first condition and second condition.
Do you know any example that does not satisfy 2 or 3? Because it seems to be very hard to satisfy.
The hardness, they are different, so
Yeah.
we hope it is true in general.
Yeah, I also.
Yeah, so but this one,
Second one. First one is we have many examples actually,
yeah,
but the really
yeah.
this condition is
yeah. So we hope this, but probably it is hard problem to prove in the algebraic geometry.
yeah. Actually, you don't know.
And polynomial. So then a polynomial. Of course, polynomials they belongs to CLM. So then this is just a product of them. So, but by definition, it is a polynomial of Ln over the complex number, but up to some constant multiplication, we can take it is a polynomial over the integers. This is a polynomial. So from here, so we want to define Reidemeister torsion quickly. This is very classical invariant. So in 1930s, so Reidemeister and Franz and Drum, they started to study this invariant. So first, I want define algebraic setting. So usually we consider a homology. So, but of course, it is defined. It can be defined for cochain complex, but today only consider chain complex. This is a chain complex over simply. For simplicity, we consider everything over the complex number. And this is just a boundary operator. And now we assume, so for any chain module, now they are vector spaces, but so then we can choose a basis of their vector spaces there. So then we consider a based chain complex. We have to assume so a cyclicity. So C star is acyclic. That is this is definition, that is all homology of this chain complex is finite. So, namely, all cycles that is isomorphic to the boundary. So then, now this is an image of CQ. This is cycles. So now, from the acyclicity, this is isomorphic to the boundary. Now we put basis of boundaries. So it gives a basis for the cycles, and now we have a basis for chain modules, and of course here we have another one, so BQ minus 1. In some sense, so this one, so in geometric setting, so this one is coming from CW complex structure. So, but to define the torsion, we need to fix the basis of the boundary. So, but finally, so torsion, it is not depend on the choice of basis of the boundary. So, but to define, we need it. So then, of course, this is short exact sequence. So then, now we consider the image of BQ. That is some subset of vectors, and we take a lift. So we have. So this is the exact sequence, short exact sequence. So then, pair of BQ and a lift of BQ minus 1, it gives another basis of CQ. So then we can consider transformation matrix between them. Transformation matrix between them. So, and we write square bracket to its determinant. This chain complex. To do it, we need a basis of chain modules. So, but now we fix CW complex structure. So then, for example, I cells in M. So we write U1 UD. They are I cells in M. We take a lift I cells in M children. U1 children UD children. We choose one lift for one cell in M. And for V, we have a canonical basis in BC2. So then totally generator, the basis of the ice chain modules is U1 tilde tensor E1, U1 tilde tensor E2, U2 tilde tensor E1, UD tilde tensor E1, UD tilde tensor E2. So it gives the basis for this space. So then, if this chain complex is acyclic, then so tau rho n is defined by the torsion of this chain complex. So if it is not acyclic, then in this talk simply we define torsion itself. Of course, so if not acyclic, we choose some basis of homology. At that time, so we can define this invariant. So, but for the moment, so in this talk, so simply we define it is therefore the non-acyclic representation. So when we consider the real algebra coefficient case, at that time, of course, as I said, so homology, or for homology, it is related to the tangent space of character variety. So then in some sense torsion, it is differential forms on character variety. So then to study such a thing, it is a very interesting problem. So many people now working on such a subject. For example, so recently Julien Marché in Paris, or his student Leo Bernard, they are working on such a subject. So then I explain character varieties, A-polynomials, and torsion. Okay, so then tau rho n, tau rho prime m, rho is conjugate to rho prime. So then tau gives a function on xe, xe and to c. So it is better to write again its main cell. So statement is the following. So we have two nodes. Suppose they satisfy the following. So for any irreducible component C in X in Ki. Dimension is 0 or 1, and if dimension is 1, then the image of C in X boundary E Ki is not a point. This is the first condition, and the second condition GCD of AK1 M and AK2 ML is trivial. Then RT sigma K1 K2 is a finite. This is a statement. So to prove this, in fact, we have to discuss along. So to prove this, in some we discuss about the image of the Reidemeister torsion. So now sigma K1 K2, this is the splicing of K1 and K2. So now we have one irreducible representation now we only consider irreducible one. So this fundamental group of course it can be described as the amalgamated product of phi1 ek1 star over phi1 p2 Now we can see this dilemma. If law is irreducible on phi1 sigma k1 k2, then restrictions on phi1 ek1 and phi1 ek2, they are also irreducible. And second lemma. So law is acyclic on total group, a total space. Then law is acyclic on phi1 This lemma, by using this lemma with the following well-known property of the torsion. Usually we call it Meyer-Beatrice argument of the Reidemeister torsion. So let M simply will write a splicing case. Lobier representation. Take this better. Sigma K1, K2. SL2, 3. This is suppose row list on Pi1 T2. No. Okay, simply we like this is a cyclic representation. So then by using this lemma, automatically, so row Pi1 T2, it is a cyclic. So then claim is Pi1 row restrict to Pi1 EK1 and row Pi1 EK2, they are acyclic. And tau row M, tau sigma K1, K2, it is a product of tau row EK1 times tau row EK2. So now we consider irreducible representation of the splicing. So it gives a acyclic representation on the torus. So and also it is irreducible acyclic representation on each part. So and the torsion, it can be split into the product of each part. So then,
so the row on each part are acyclic. Are they condition or consequence of a previous condition?
Okay. So this is condition.
Yes.
This is consequence. Yeah, because simply we like K1 plus K2 or to is the if we consider exact sequence of chain complex, we know this part is acyclic, and also we know this part is acyclic. So then automatically this is they are cyclic complexes.
So in general, in the formula,
yeah,
it also involves some determinant of grain map.
Determinant of what?
the
H.
following map H.
Yeah.
But here, that part is just trivial because
Yes.
by
Yes.
definition of the.
Yeah. So I have skipped. So, but now we only consider SL2C representation. The tau rho T2, it is always trivial.
Yeah.
Yeah. So then, in general, so tau rho total space times tau rho T2 is this product.
I'm saying that also in general that depends on the map H. But here.
Following map.
Yeah. Yes. Right. Yeah.
In this case, we fix H by meridian to longitude and longitude and meridian.
Okay. So I am confusing. Yeah. So this is just only consider splicing. So then special map.
Yes.
So then by use, I want to use this formula. So then we want to see the finiteness of the values of this. So, but if we could see the finiteness of the values of each part. So in some sense, it gives the finiteness of sigma k1 and k2. So it means, so now on the character variety level, this, so in general, this has a positive dimension, and we restrict x is k1 or k2. Now here, so dimension is 1. The image of this character variety in these character varieties of not space. So then if image of x is sigma k1 k2 in x is ki, if it is a finite set, then of course, so we have only finite choice of representation for these not spaces. So for the total sigma k1 and k2, the torsion, it is a product of them. So then we get the finiteness of RB sigma k1 and k2. Yeah.
So it seems that you actually prove the finiteness of representation. Finiteness of representation.
Yes, right. Yeah. So this part dimension is positive. So, but the image in this space, it is a finite. So then totally we can get the finiteness of the image of the Reidemeister torsion. Okay, so outline of the proof. polynomial of variables L and M. If zero set of F and G, this is a subset in C2. It is a finite set if and only if great common divisor of Fg is trivial. We can see this. So we apply this lemma to A-polynomials, and also we have to discuss next one. Let this be a regular map between their affine algebraic set. So, and also if dimension x is 1 and x is irreducible, we apply for character varieties and projections. Then F inverse of 1 point is a finite set for any y. How to use this? First, we consider the subspace in C2. It is the zero set of LK1 LN equal LK2 ML equals 0. So this is algebraic curve. This is an algebraic curve in C2, but now we see a great common divisor is trivial. So then by using this lemma, so this is a finite set. So then we write L, J, and Mj. Equal 1 to M, something like this. So then this lemma applied for this point, we consider the inverse for this point. So we take inverse in character variety of the splicing. So, but to apply this lemma, so we need every irreducible component is dimension 1. So, but the inverse is a finite set. So then totally, so we get RT sigma K1 and K2 is a finite set. So finally, so I want to mention something. So then now splice manifold. Now we're considering splicing manifold. So then now we see for two bridge. Case it is okay. So but for higher bridge number for n bridge. How about this? That is the problem. So as I said, I mentioned before, so Forti and Paolotti, the examples, that is one tensionous knot. So connected component of character varieties has a higher dimension. So for several examples, we computed so RT sigma so that is not proof, just for observation for some examples, but many examples it is a finite set. So this case, so character variety has a irreducible component with
second last line.
Yes.
Yeah, there is a finiteness.
yeah.
How do you get to the last conclusion?
Actually,
So
this one, I
maybe
think.
now so XL just a moment. Yeah. Okay. So now we consider this algebraic set.
Yes.
So this is a finite set
Yes.
in C2. So but now now we have 1 point L1 and M1. So we want to see the inverse of this point.
Mm-hmm.
It is just 1 point in here. So then now in some sense this is of course isomorphic. So then this map is we write R and theta.
Yeah.
So then this is just X and this is just Y. So then now we assume any irreducible component of this. It is at the most dimension is 1, and then we can apply this. So 1 point, the image, inverse image, it is just 1 point. So yeah, now we want to remove if some component. So if it goes to 1 point,
Mm-hmm.
so the argument it doesn't work. So but we can see by using such a lemma. So inverse derivative of the 1 point is just 1 point.
So dimension of x is you assume that 1.
Yes.
And I think you use the meridian map is regular map. Use the fact that
Yes,
Yeah.
right, yeah, right.
so by the condition the gluing, so we have some value of meridian,
Yes,
then the preimage of that meridian value should be
yeah,
finite set by
yes,
this
yeah.
lemma, I think. So that's the
yeah.
I think so. I think that's the proof. Yeah, a part of proof. I
Yeah.
think, yeah.
Mm.
But Reidemeister torsion is defined on whole x.
Whole x, yes.
But
Whole x,
the
but so
actually finite set. Defined on finite set.
But the dimension is 1.
No. So the dimension of x is the dimension of not complement, but we want to define torsion on the splicing manifold. So when you look at the splicing manifold, the half is some restriction of original not complement of character variety.
Yes.
So that restriction is just by the dysregular map, because we can take only finite choice of meridian on the whole character variety. So actually he proved that the dimension of character variety is finite.
Dimension of
Character variety is finite. Actually that's what he proved.
character variety of what?
Splashing manifold satisfying this condition. Character variety of M.
Yes.
So M satisfy this whole condition.
Yeah.
But in the beginning, he mentioned that by the result of other
Yeah.
people.
Of course, character variety of sigma k1 and k2
Yeah.
so has a
He said that it has a positive dimension.
No. In this setting,
But,
no. So you mean character variety of this?
Yeah.
yes.
Yeah, of course it has positive dimension.
Yes.
So because yeah. So in some sense, so here is the k1 and here
Yes.
is the k2. So now okay. So simply we consider two bridge case.
Yes.
So the character variety of k1 and k2, dimension of them,
Yeah.
that is 1.
Yes.
So but totally dimension is 2. So because we can apply bending construction along these torus. So then if we take one representation for all space, but so for example we can write something like this.
Yes.
So but here that is a variant group.
Yes.
So then
Yes.
in some sense,
You're right.
yeah. So we can consider something like this modification. So then plus one dimension we can see.
Yeah. Yes. I confused something.
Yeah.
Also.
Then why? So that the character variety of the glued manifold,
Yes.
splice manifold is, you said that
Positive dimension.
positive dimension.
Yeah.
Then how do you get the last conclusion from the previous fact?
Yeah. So we have one representation.
Mhm.
So of course, near this representation, dimension is 2.
Yes.
So we consider restrict to simply like Q1, Q2.
Yes.
So they are finite sets in each character variety. That we can prove.
Mm-hmm.
Okay. Now I understand. Yeah.
So then,
Yeah.
so we have only finite
Yeah.
conjugacy classes of each character variety of knots. So then here we apply
Formula. Torsion formula.
yeah.
Product. Torsion.
Okay. Yeah. Okay.
So actually, you prove that the dimension of character variety occur by the bending. There is
Yes,
only
yeah.
the bending pact. The other pact, there is no other pact of making the
In
dimension.
this splice setting, so yes.
Yeah.
Yes.
Okay. Okay. I see.
Okay.
Any other questions? Unless, thanks to speakers.